Professor Nakana.
Yes.
I'd just like to clarify, we are allowed to use like a secondary tablet or laptop if you want to view the textbook PDF, right?
Yes, that's correct. Yeah, so the only thing is, I don't want you, I don't think it's that productive necessarily to go like searching around on the internet. It's just going to waste your time. So I'd rather have you, have specific resources available to you that you can reference without wasting a lot of time. Okay, I think the book and your notes, that's probably plenty. Okay, are there other questions? So did everyone receive my email today?
Yes.
Yes, okay, good. Were the instructions fairly clear? I mean, we had gone over it before. I just wanted to make sure that there's nothing really ambiguous there. Okay, I guess it was fairly clear then. Okay. Okay, let's see here. All right, can everyone hear me out there?
Yep.
Okay, great. All right, so I don't know if I had everyone online before, but did everyone receive my email? Anyone not receive my email?
Yeah, I got it.
Okay, good. All right, so I hope that the instructions were fairly clear. I'm not exactly sure. I mean, I haven't done this, the final before online. I've done other tests online, but with more people, there could be more confusion. So, I mean, we'll have to definitely sort of, be flexible and play things by ear sometimes. But I think overall, there's a fairly reasonable plan in place to hopefully, hopefully get through the final successfully and everything. All right, without too much stress. Okay, so I'd like to continue the review, and I'll leave some time open at the end probably for questions. And then on Wednesday, I plan to just finish up the review and then open it up to questions then. Okay. All right. So the first thing I want to talk about today is the notion of subspaces. All right. All right. So the idea is as follows. So we have W, subset of Rn. So a subspace looks like a plane, for example, which actually goes through the origin. Okay, so this is like W over here. And so what properties do we need for a subspace? Well, we know that when you take vectors, you can add them and then you can multiply them by a scalar. So basically we want the operations to be closed in this subset. So W is a subspace of Rn if and only if one, if V1 and V2 are in W, then V1 plus V2 is also in W. And two, if lambda is a scalar and V is in W, then lambda times V is also in W. Okay, so maybe there should be an if over here too, right? Okay, any questions on this? Now, the nice thing about subspaces is that they always have bases. So every subspace has a basis. And two, different bases for W have the same number of elements. Okay. So because they have the same number of elements, I could talk about the dimension of a subspace. So the dimension of W is equal to the number of elements in a basis for W. Okay, so these are three very important principles about subspaces and bases. All right, any questions up until this point? All right, so let me just remind you about a basis. So V1, V2 up to Vt is a basis for W if and only if two things happen. So what do you have to check in order to have a basis? Anyone?
If
It has
the
to go
entire-
through 0, the origin.
What has to go through 0? What properties do you have to check for a set of vectors to be a basis?
Set of vectors are linearly independent.
Good. So first thing is they have to be linearly independent.
And W has to equal the span of the vectors.
Good. So W has to be the span of the vectors. So every vector is a linear combination of these vectors. Make sure you have this definition down. I mean, I guarantee you, you're going to be tested on this. All right. Okay. So you should be able to, if I give you vectors, and this has happened on the midterm, you should be able to check whether they're linearly independent or not. And you should also be able to check whether, a vector is in the span of the other vectors by looking at the system of equations. Okay, so again, I'll reiterate, for linear independence, you're looking at the solution, I guess I want to call it AX equals 0. Okay, and you just want to make sure that when your vectors are in the columns of A, you only have the trivial solution. So A consists of the vectors V1 up to Vt in the columns. Okay, and then spanning, you have to look at AX equals B. And so, of course, you're looking at the system of equations like this, and whether it has a solution or not. Okay, so we've gone over this several times, but I'm not gonna, I mean, you should definitely review it if you're not too confident about this. Okay, any questions on this?
For the span, is it a unique solution or can it be infinitely many?
There could be infinitely many.
Okay.
I mean, for example, suppose that you have like, I mean, you have more elements than you have in the dimension. Then you're gonna have infinitely many solutions, right? Conceivably. So, if you don't have a basis, I mean, if you have a basis, the solution is gonna be unique. But if you have, more vectors than you need, then you could have redundancy. Does that make sense?
Yes.
Okay. Yeah. Okay, other questions? All right. Okay, so let me just write this down. I hate to harp on this, but let me just say, you should know how to check the following. Linear independence, okay, spanning, and you should also be able to check whether something is a basis. So, you check whether they're linearly independent and whether the vectors span, okay, and if those two things happen, then you know it's a basis. Okay, any questions so far? All right, now there are certain subspaces that came up very naturally, and I just want to review a little bit how to compute those. Okay, so let me call this specific subspaces. Okay, so the first one is, so I'm going to start with A being an m by m matrix. All right. So the two subspaces that we looked at were the column space and the null space. So let me recall the column space of A. This is the span of the columns of A. All right. Now, what we did was we actually gave a procedure for finding a basis for the column space. So how did we do that? Well, we took A over here, and then we transformed it into the upper echelon form. So this is in the echelon form. And then what did we do? So you can look something like this, right? So it's an upper echelon form, and we located the pivots. Okay, so we locate the pivots. So these are the first non-zero entry on every single row. And then what we do is we locate the columns here. And then we go back to A and we pick out those columns. Okay, and then this forms a basis. So these columns of A form a basis for the column space of A. All right, so we can use Gaussian elimination in order to find a basis for the column space. All right, and the dimension of the column space is equal to the number of pivots. Okay, any questions on this? All right, and then what we did was, and we've done this like a zillion times, we actually have the null space of A. And this was the set of homogeneous solutions. So let's see, so this is the set of X in, let's see, number of columns, so Rn, such that Ax is equal to 0. Okay, it's just the homogeneous solutions it's the solutions for the homogeneous system. Okay, and so how did we find a basis for the null space? So what we do is we just transform, well, let me just say it this way, sorry. This is not quite the way I want to say it. Okay. So basically you solve the homogeneous system. So what are we doing? We're taking A and then we put the 0 vector here and we transform this into U and then the 0 vector over here, right? And then you actually get your solution set as maybe S1 times X1 plus S2 times X2 plus, let's say, S sub R times X of R, where S1, S2, and the SRs are free variables. Okay, remember the free variables correspond to the places where you don't have pivots, right? Okay, so then you take these X's as a basis. For the null space. Okay, so we've done this many times, so I hope that it's pretty clear how to do this. Okay, any questions so far on this? All right, so what I'd like to do next is I'd like to go over determinants. Okay, so that's second topic of the day. Okay, so this concludes subspaces for now. So 2, we're going to talk about determinants. Okay. So what was the idea of a determinant? So if I have a n by n matrix, I want to actually know whether I can invert the matrix or not. So we actually want to be able to compute a number which tells us whether we can invert the matrix or whether the matrix is invertible or whether the matrix is not invertible. All right, so how do we do this? Well, let me just start off with the 2 by 2 case. All right. So we have a formula for the inverse in the 2 by 2 case. So if A is going to be equal to A, B, C, D, what's the inverse? It's 1 over AD minus BC And what do? You flip the D and the A and then you negate the B and the C. Okay, so this is the formula for the inverse. And we know, you could actually see from the formula that the inverse exists if and only if AD minus BC is 0, not 0. So A inverse exists if and only if determinant of A, which is equal to AD minus BC, is not equal to 0, right? Okay, so what happens with in the n by n case? Well, you can actually generalize this, right, as follows. So you can define the following. You can define the cofactor Cij to be equal to -1 to the I plus j times the determinant of Aij. So Aij is the submatrix of A obtained by deleting the ith row and jth column. Okay, so we've seen many examples of this. And so what it allows you to do is it allows you, if you have a 3 by 3 matrix, you can actually try to write the determinant in terms of a 2 by 2 matrix and its determinants by using the cofactors. So the determinant, it turns out, can be obtained by expanding along any column or any row. So you have A1J, C1J, plus A2J, C2J, plus ANJ, CNJ. Okay, so this is a column expansion. Okay, it's along the jth column. And it's also equal to expanding along the rows. So AI1, CI1, plus AI2, CI2, that's a 2, plus AIN, CIN. So this is a row expansion here. So you can expand along any row or any column to actually compute the determinant. All right. So here are some things that you should know how to do. So you should be able to know how to compute determinants in several different ways. Okay. So the first thing you should know is you should know the formula for the 2 by 2 and 3 by 3 matrices. So they're explicit formulas that you can use to actually compute the determinant. The other way you should be able to compute the determinant is row or column expansion. Okay. And then the final way is you can use Gaussian elimination. To compute the determinant. And so the determinant of A is going to be equal to 0. I'll just say it's -1 to the R times the product of the pivots. Yeah, I should just write it out. Sorry about that. I messed up again. So this is the product of the pivots. If there are n non-zero pivots. Okay. And if they're not, it's going to be 0. And here R is equal to the number of row exchanges. This is product of the pivots. Okay, any questions on how to compute determinants? All right, so there are a few other rules. So you should remember that when you take the determinant of the product, it's the product of the determinants. Okay. And if you take the determinant of A, it's the same thing as taking the determinant of A transpose. Okay, so those are common rules. And then one thing you should know how to do is Cramer's rule too. So if you have a solution, AX equals B. So the nice thing is a lot of this is in the book. So, you know, if you don't have to memorize everything. You should just be aware of these kind of things. And if you need to apply it, you can actually use your book if you need to. So the point is that with Cramer's rule, you can actually find the solutions by using the determinant. So if I have X being a solution, X1 up to Xn, then the Xi's are equal to the determinant of AIB over the determinant of A. Okay, so AIB, what do? You just stick B in terms of the ith column. So it's the columns of A, but then you put B into the ith column. You replace AI by B, and then you just take the determinant. Okay, so you can see that if this works as long as the determinant is not 0. So, you know, the theorem, of course, is that the determinant is non-zero if and only if A is invertible. All right, so I'm not going to go over this, but you should also know about volumes. Okay, so volumes of parallelepipeds, okay, and how to actually compute those. And then there's also a formula for the inverse. And then you can compute inverses of matrices by cofactors. Okay, so let's see. So let me just say it this way. So if A is invertible, A inverse is 1 over the determinant of A. And then you can just compute the cofactors, but remember you have to take the transpose. So it's C11, instead of 1, 2, you have 2, 1 here, CN1. C12, CN2. Yeah, that makes sense. Okay. And then finally, C1n and then CNN. Okay, so make sure you transpose the cofactor matrix in terms of the AIJs. All right, let me pause for a second. Questions about determinants? How to compute them, what they're good for. Okay. All right, so I just want to cover 2 more topics today. So one quickly is the LDU decomposition. Okay. So so let's say A is a m by m matrix. Then what I could do is I could sort of factor A in terms of L times U first. So if no row exchanges are needed, okay? And the U prime is just the matrix you obtain from Gaussian elimination. So U prime is in sort of echelon form. Okay. And the L is an n by n matrix, which is invertible. So L is an n by n invertible matrix. And you obtain this by just taking the multipliers and sort of looking at the negatives of these things. So let me see, how do we want to do this? We'll just do an example later on. Okay, I'll give you an example. All right, so this is a matrix obtained by looking at elementary matrices. Okay, and then you can factor U prime in terms of D and U, where U prime is in echelon form with the ones as pivots, and D is a diagonal matrix. Okay. So I don't know, maybe, I don't know, do you want me to actually go over an example of this? Or, I mean, I think we've done this enough. I'll just give you an example to do at home, okay? So here's an example, practice example here so that you can practice doing this, right? So let A be equal to 1, 1, 1, 1, 4, 4, and 1, 4, 8. Okay, so the problem is to factor A as L, D, U. Okay, so you use Gaussian elimination, you keep track of the multipliers, and then your L matrix will be the negative of the multipliers, put in the appropriate positions. And then once you get down to the U prime, you can sort of pull the entries, the pivot entries off to form D. And then to get U, you divide by what you factored out by. Okay, any questions on this? This is considered a very standard problem, meaning that it could appear on the final exam. So, all right. Okay, so let me cover inverses, and I'll actually give you a problem to do. So that's the last topic, and then I'll open it up for questions. Okay, so this is called inverses and transposes. Okay, so A here is a n by n matrix. Let me say n by n matrix. Okay, so it's square. So we know that A has an inverse if and only if there exists a B such that A times B is identity and B times A is also the identity too. Okay. And one of the things we actually showed was that once you have this property, any matrix has to be, I mean, it's unique. So we can actually say that B is actually equal to A inverse. Okay. All right. So in terms of inverses, there are two procedures. So we can find inverses via Gaussian elimination. Okay, so that's one way we can actually find inverses through Gaussian elimination. I'll go over that in a second. And then the second thing is you can use cofactors. And I stated how to do that. Okay. So for the way to do this for number one, so let me just write this down, is what you do is you start out with putting the matrix A over here, and then you put the identity on the right-hand side. And then you perform Gaussian elimination and you transform A into the identity, and on the outside, the I part, you're keeping track of how to find the inverse. So you use Gaussian elimination here, and you transform this to the identity, and this is going to be A inverse on that side at the end. Okay, there's several examples, we've sort of done before for this problem. Right. Okay, so I don't know if we have time. Might as well do one. So let's do an example of this. All right. So here's the problem. So find the inverse of A, and it's 2 minus 1, 0, and it's minus 1, 2, minus 1, and we have 0, minus 1, 2. Okay, so we want to find the inverse of this matrix. All right, now we can use cofactors if we want, but let's actually do this using the Gaussian elimination method. So again, you put this on this side, and then you put the identity over here. Okay. All right, now I can actually just multiply this one by 2. And we have 2 minus 1, 0, 1, 0, 0. And then what do we get? We get 0, 3, minus 2. And then we get 1, 2, 0. Okay. And then we'll keep the last row the same. And then 0, 0, 1. Okay, so now, you could divide by 3 already, but then you have to work with fractions. So instead, let's just do this. So you have 2 minus 1, 0, 1, 0, 0, 0, 3, minus 2, 1, 2, 0. And what are you left with? You're left with 0, 0, and then 6 minus 2 is 4. And then you're left with this one and that one. So you get 1, and then you have a 2, and you have a 3. Okay. And now what you want to do is you want to eliminate this one next. Okay. So you're going to multiply this whole thing by 2 over here. So we have 0, 0, 4, 1, 2, 3. And then what do we get? We get 0, 6, 0. And then I get a 3. And I get a 2 plus, I get a 6. And I get a 3 here. Okay, and I have a 2 minus 1, 0. So we're almost done. Because everyone's kind of seeing what we're doing. And then finally, I want to get rid of this one over here. Okay, so let's multiply this row by 6, add it to the second row, and then I think we'll be almost done. Okay, 0, 0, 4, 1, 2, 3, 0, 6, 0, 3, 6, 3. Okay, so what do we get? We get 12, and we get 0, and we get a 0 here, and we get 6 plus 3, that's 9, and we get a 6, and we get a 3. Okay, and then you basically just divide the first row by 12, and then divide the second row by 6, and the last row by 4. All right. So then you divide by 12, and you divide this one by 6, and you divide by 12. By 4, sorry. Okay, any questions on how to do this? All right, while we're at it, let's just compute the determinant of A. Okay, so let's just compute this out to see what we get. So it's a symmetric matrix like this. Okay. So there's several ways we can do this. We can either use cofactors, or we can just use the formula that I gave before. So let's do the computations using the formula. So basically, you just want to run down the diagonals and see what we get. So we get 8. Okay, this one, this one, this one's 0. This one, this one, this one is 0. Minus this one, this one, this one is 0. This one, that one is going to be 2. Right, so it's minus 2. And then this one, this one, this one is what? Again, it's a 2. Okay. So I get 4 for the determinant. All right, any questions on how we did this? I would say, the final, a lot of it's computational. So, make sure you have the computations down pat and make sure you check your work. You should have plenty of time to actually do that. Okay. I just wanted to give you some concepts that you should review at the end. So here's some concepts that you should be able to work with. So one is linear independence. One is, of course, linear dependence. You should know about spanning. You should know about, again, inverse of a matrix. You should know about linear transformations, which we'll go over a little bit next time. You should know about bases. Let me put this up here because it's more, sort of with linear independence. And then the idea of a subspace. Okay, so this kind of all goes together. Determinants. Eigenvalues. Eigenvectors. Okay, so then there's a null space, column space, rank of a matrix, which is the dimension of the column space. And the dimension of a subspace, so. Okay, so, I would, if you want to create some index cards, just so that, if there's a concept that comes up on the test, you could just flip to an index card. I'm very happy with you doing that. Because, I may ask you for the definition, or I may ask you to actually use the definition to solve a problem. Okay. Questions? I'd like to open it up generally. So that's the end of my review for today. So I'd like to open it up to questions about this material, or even the material prior to this.
When we're calculating determinants, are you
Yeah.
gonna specify which way we should do it, or is it up to us to choose?
Okay, that's a very good question. So I may specify the method, all right? If I don't specify the method, you can use the method of your choice.
Okay, thank you.
Okay. I hope the wording is fairly consistent with the midterms, midterm 1 and midterm 2. So, I don't want to like change things up too much on you guys. I mean, you sort of get used to a professor's way of doing things, and I don't want to throw you any curveballs or anything. So, but if you do have any questions on the exam, you can either raise your hand or shoot me an email, and I'll try to answer as soon as I can. Okay, any questions? Sorry, let me go back to. So no other questions?
Yes, I had a quick question.
Sure,
We didn't
Brad.
really go over anything with like change of basis, I don't think, before the
Yeah,
final.
so that's a good question. So what I'm going to do is on tomorrow, I'm going to actually kind of clue you in on what I expect on in terms of that. In some ways, doing eigenvalues and eigenvectors, you are changing basis, but I don't know how much I'm going to emphasize that. So maybe some of the basics, but not something, incredibly deep. But I will actually go over some of that on Wednesday.
Okay, thank you.
Yeah. Thanks for mentioning it. Oh, yes. And let me mention, there's some other applications that I'll probably mention tomorrow too. But, again, those are from the prior tests, like, balancing chemical equations and networks and economic systems. So those are sort of the first applications that we actually did using linear algebra. Okay, other questions? Okay, so if not, I guess we're going to stop. And then tomorrow, like I said, I'll tie up some loose ends. I'll again leave time for you to ask questions on the material. Or if you want me to, kind of give you some ideas about problems or anything related to the course, I'm happy to do that tomorrow. Okay. All right, great. Okay, so we will see everyone tomorrow at the same time. Okay, bye-bye.
Thank you.
You're welcome.